starting material for our experiments is actually old lava, well, or like lava anyhow. It's basaltic material, this gravel. It comes all ground up. Looks like it came out of your driveway almost, but it's special material. It comes from down around New York City, just north of New York City, from the Palisades Sill. If you go drive across the George Washington Bridge to the west toward the New Jersey side, you see the big black cliffs there. That's the Palisades. The Palisades are a large body of basaltic material, and we've gotten this material from a quarry that's located within that Palisades Sill. It's a very uniform, very well characterized kind of basaltic material, and here you can see the final product, one of our lava flows from recently. It's nice black glassy material, so the old basalt has become new basalt here. In addition to the material from the Palisades Sill that we melt, we also use material from northwestern Wisconsin, basalt from what's called the Mid-Continent Rift. It's about 1 billion years old, and it comes from a giant crack that opened up in the earth, a giant rift valley like the East African Rift. The Palisades Sill also opened up in that type of a crack. Both of these are basaltic rocks that are typical of rift settings. In the early days of the Syracuse Lava Project, we started out using a very small floor furnace. It had a crucible that was about the size of a big wastebasket. And this crucible, which is made up of silicon carbide, was heated up to about 12 to 1400 degrees centigrade. Some of the student helpers and Professor Wysocki had to lift up that crucible with a crane and then manually pour it out. Obviously, we couldn't control our experiments very carefully that way, but these were our first experiments, and we were able to demonstrate some of the diversity of things that we could do with our project by melting this lava. We graduated to a much larger size furnace.
This has been the workhorse of the Syracuse University Lava Project. It's a natural gas-fired bronze furnace I picked up used in Canada, and we've rebuilt it to make lava. It has a ceramic lining, ceramic-like lining. It's a crucible made out of graphite and silica sand. It withstands temperatures of 3,200 degrees Fahrenheit. It's lined, so that would be that ceramic portion inside. The lava is actually, that's where the lava is melted and contained. There's a chamber that's about 6 inches wide that runs the height of this. And then this steel jacket is lined with refractory. Refractory is a brick-like material. It's very similar to the material that is at the bottom of the fireplace. It takes about 24 hours to take crushed basalt, rock, and melt it into 800 pounds of lava. When we want lava out of it, we take the cap off and exposing the spout. We also take the dump out door off, and this is just a side note. This isn't the case. We lose the furnace, we lose the crucible in here. It cracks or something. This is a place that the lava in the middle of the night when this thing is running is able to try flow out and not cause any damage to the rest of the machine. So it's kind of a safety valve for the furnace. And this thing tilts over just like this. You can see up here, this is a lid that we have secured here, but when it's upright, this lid swings off to the side, and this is how we add fresh basalt to the crucible in here. And it's also how we, when we inspect it when it's running, know what temperatures we're hitting and so forth. So, as I said, this machine's great. This natural gas-fired furnace, it hits 2,750 degrees Fahrenheit. It's great for the scientists. But that 800 pounds wasn't enough to do what I want to do within my artwork, which is to create geologically accurate in terms of scale as well as form and content lava fields or lava flows. My interest is creating one, say, the size of a basketball court, the size of a football field, the size of, an acre in size. I needed to go much bigger and much faster. Here in the art program, we have a smaller version of this. It's an iron blast furnace. It's coke-fired. It hits much hotter temperatures, around 3,200 degrees Fahrenheit. And we weren't sure at first when we tested it how it would work. We didn't know if it'd be a continuous flowing thing or if the bottom would just fill up and it would be similar to the gas-fired furnace. In June of 2012, we had our first test firing of, as I said, much smaller, and it flowed continuously for 45 minutes and put out 600 pounds. The way this works, it's very simple. There's pieces of coke, which is fired off coal, it's a stack of it in there. For today's demonstration, only 2 of the 6 pieces are here. This is much taller. It's actually 15 feet tall. And there's a pile, it's known as a pile of coke in there. And it's not just coke, these chunks of coke that are the size of a cantaloupe thrown in. They're actually placed strategically up to about half the height of this. And then there's more smaller pieces of coke put on top of that. When this thing is ignited and it's up and running, there's forced air, regular atmospheric air we breathe, is pushed through these 6 pipes. They're called tuyeres. And so it's once you get the coke to ignite and burn on its own, with the introduction of the forced air, you see temperatures, as I said, well above 3,000 degrees Fahrenheit. And it takes a couple hours to get the whole thing heated up to do that. And at that time, we closed this with a big piece of clay in here called a bot. And this holds back anything that melts. And it's to keep the heat in there as we reach this much higher temperature, around 32 to 3,500 degrees Fahrenheit. Now, I mentioned before it only goes to 3,200 degrees. By introducing oxygen and acetylene, we boost the fuel much higher temperature, and we'll be able to melt a great deal more in here. As this stuff melts, this begins to slide down or move down in the combustion chamber, and it's actually through these tuyeres, and there'll be a piece of heat-resistant glass here, you can actually see the lava inside. It looks as if it's raining in there, lava. It's amazing. And that collects down here. Then we'll tap this. We'll get this piece of clay out of there, and this thing will run continuously as long as we keep adding coke and material, unmelted material on the top. It'll run continuously 24 hours a day for a week.
So we have 2 main objectives here: to document the lava flow behavior and then to match the shapes of lava flows that we make with those that we see in nature. We'd love to be able to go to lava flows in ancient geological terrains and be able to say how those lava flows formed. To do this, we often change one factor we think is important and in which we're interested in, and sometimes we change it incrementally or in large steps to see how it affects the outcome of our experiment. In science, we do experiments over and over again to replicate our results to make sure that an individual result wasn't just a fluke or perhaps was influenced by some sort of factors that we didn't understand. In the following sessions, we're going to be using our experiments here at Syracuse University to illustrate some of the behavior of lava and to give you a chance to see exactly how this material behaves as we vary different parameters in these experiments.